Today I am presenting my master's thesis work, and we have given a methodology to calculate e-readiness, and we have used an approach which we named as divide, predict, and conquer. And currently I am engaged in Novel Prasi. I am engaged in one of the colleges from Novel Prasi. The table of contents are, first of all, we will discuss about what is divide and conquer approach, and then why we are using prediction, and what is e-readiness, and its importance, and why we are using this approach, and conclusion. So first of all, what is divide and conquer? Subproblems of small sizes, and we do this recurrently until we do not achieve a base case. And what is the base case? It is the smallest subproblem whose solution is defined for the machine. This is used by computers. And finally, when all the base cases are solved, we use to conquer them. So here I have taken an example, and we take a small instance of integration, and suppose we have four rules defined for our machine, and suppose we are trying to solve this equation or this expression. So what actually the computer do is it uses the rules. It searches for a rule, for a particular rule to apply over the expression. And you can see here, we can apply rule 4 here. What rule 4 is saying? It is saying if a fx dx, then it can be written as a integration fx dx. So we apply rule 4 here, and similarly, the same problem, after next step, we divide it again into two subproblems, and we do this process until we do not achieve base cases. So divide goes in the bottom direction, and the conquer part goes in the upward direction. So why we use predict in between divide and conquer? So here we have the problem. What if we came up with a base case whose solution is undefined for the machine? So what we do, we use prediction model, and which further gives a new problem. And the new problem is what mechanism can be applied for the prediction. But here in this presentation we are not interested in the parameters, but we are interested in the number of parameters. So let us assume we require n parameters, and we have given them name p1 to pn. This is some statistics, and we can see here Europe has the highest e-readiness index, and it is done by United Nations in 2014, and Asia lies in between. It is greater than Oceania and less than America. And what is the importance of e-readiness? I try to relate it with two glasses and water. So we can see here there are two societies. The size of glass is the society, and the flow of water is technology. Now, flow of water is constant, but the size of flow of water is constant, but the size of glasses are differing, and they can take benefit on the basis of their size. So, if we can consider these two as two types of society, so definitely this society will grasp more opportunity in comparison to the other one. And this measurement, how much, how a society is ready to grasp the benefits arising from technology is what we call e-readiness. So further, okay. So what we do, we use, we proceed up to similarity testing by considering P1, P2, P4 and P5 as the feature vector or property vector of municipal. On the basis of this vector, we create the clusters and we do the similarity testing of MX. MX is a particular municipal where P3 is missing. And then what we do prediction for P3 for MX. And this is done on the basis of multiple linear regression. And what we get after doing this multiple linear regression, we get an approximate value of P3. And then we can concur the result. We can concur all the results to get the national e-readiness. And this methodology is very good for countries like our, because we know that there are unpredictable diversity in our society. And for future work, we have decided to calculate e-readiness of a district. These are the differences.
The title of the talk, I thought I will be telling is changes and their even vectors. तर टाइम स्क्विज गरेकोले त्यसको चाहिँ स्वास्थ्य गरेर रिसर्चरहरूले चाहिँ नि यसमा रिसर्च गर्न हुन्छ भनेर के पेपर हेरे पनि हुन्छ भने त्यहाँबाट म छोडेर चाहिँ छोड्ने मैले विचार गरेको छु. Flashback. So what even vectors are there? So I'll start with the even values and even vectors, which we know. For any matrix, we can find even values and even vector. Let A be a square matrix. How do you find A to the power 100? That means very simple answer is multiply 100 times matrix A. Possible jagat 100 times matrix A. Like 2 into 2 garula. Even 2 into 2, 100 times multiply गर्ने बेला त बिहान गर्यो भने भात खाएर छोडेर ब्रेकफास्ट छोडेर सबै गर्यो भने लाने हुन्छ कुनै थाहा छैन मलाई. It takes time. And because when you are doing lot of works, physical work or mental works, then there's probability that you will make a mistake. For example, it is simple to multiply 100 times a matrix A. For example, if I take a very simple matrix X, which is not with whole numbers, which is something like it, 0.8, 0.3, 0.2, 0.7, then how do you find 100, A to the power 100? The answer is there, of course. The answer becomes very simple like this. It will be 0.6, 0.6, 0.4, 0.4, something strange one. So you try it, but I will not take that risk of trying 100 times multiplying A. I have some other things to do. So what I will do, I will try to take a simpler way. The simpler way is this one. I have tried only two attempts. I try to find A square, which is very simple. Then I multiply again by A, I get A power 3, which is something like this, which is very now close to, you can see, the closeness is here, 0.6. Now, if you use this even values and even vectors, our life will become easier. So that's why I start from here. Matrix 100 can be found by using even values of A. Almost all vectors change directions when you go and multiply by matrix A. Certain these type of vectors are known as even vectors. So that's what we are trying to remind us from our I don't know, ISC or intermediate or bachelor's or master's mathematics. So multiply an even vector by matrix A, and the vector AX is a number lambda times the original vector X. The basic equation is, of course, everybody knows what, I am not going to read it. Back. The number lambda is an even value, so this is all we have known. The even value lambda tells whether the exceptional vector X is straight or shrink or reverse or remains unchanged. We like to say it remains unchanged when multiplied by matrix A. This is the idea behind all these things. So we want to find even value lambda could also be 0. If you have 0, then we have a big problem. Then X will be equal to 0. This means that this even vector X is in the null space. I think you all know what is null space. If A is equal to 1, it's the identity matrix, then X will be very simple, like this one. like this one x equal to x, then all vectors will have even vectors of unity I. If it is 2 into, it is 1, 0, 0, 1. Then all even values also will be, value of delta will be equal to 1. Very simple one, we have learned it too much. So, to find even values and even vectors, we use this determinant form because it has to be, lambda is an value of A if and if this value is equal to 0, because we bring both to the left hand side, we make it 0, then we find the value of determinant. From here we find lambda, putting value of lambda, we find a condition. If you find such a condition, this will be equal to 0, then we'll have Ax will be equal to 0, and we'll have Ax will be lambda x, such that this is x, this type of vector which makes it 0 is known as even vector x. So in this example which I have cited, so in this case let's find even values and even vectors. If you take this example, determinant is very simple. You write minus lambda, you write minus the diagonal, you simplify it. It has two even values, lambda is equal to 1 and then lambda is equal to half. These two numbers makes this vector singular. It will be equal to 0. So if I do like this, its even value will be 1, as in the previous case in our small example. And there is an even vector with even values 1. All components which are less than or equal to 1, because it is probability matrix. So probability matrix, I will not go through that. This I will skip here. This is not part over here. But because now, since I said when we will go to galactic, then we have what is known as big data. Recently I was in India, also in Delhi, for in the World Science Fair. I made this presentation. Also, some time back I made at KU and also Department of Mathematics about what is gravitational waves. Because it is related with what is known as gender. This is, gravitational waves is a discovery known as discovery of century. Albert Einstein put this general relativity in 1916, and gravitational waves theory is behind this equation, and it is in 2016, after 1 century, that the gravitational waves were definitely discovered physically after 100 years. Co-prediction was done 100 years back. And you can see more vectors, and you make big vectors. Vectors are matrices, and tensors will be a compact of all these matrices. This material has been taken out from this notices from June, July 2016, not too old over here, though we are already in 70. Here they will see tensor, and here I try to make some presents, but I found that if I make a present over here, everybody will be sleeping. It's very high mathematics. So I thought that I should just put input to those who will be something over here. So this is the over here on page 604, you will get here. The article itself look like this, and by bonded troops. You can go, it's a free there in the notices. You just write that volume, notice the AMS, write the volume numbers, and here you will get this whole free of cost. You can download it, the title is here. But the idea of tensors and even values, or even values, idea of even value for tensors was given for the first time by this mathematician, in the science direct mathematician in 2007 by Li Queen Key. He is from Hong Kong, so you can also download this, and then you can now, somebody next time, with 1 year or 2 years, can make a presentation on behalf of me to try to see how do you calculate even vectors for a tensor. So I think I have here some promotional material over here for you. Thank you very much.
Abstract. In 1922, the Polish mathematician Stephen Banach established a remarkable fixed point theorem known as Banach contraction principle, and after this it has written BCP, that means Banach contraction principle, and it is also known to be the Banach fixed point theorem, BFPT, which is one of the most important result of analysis is being used to solve various problems and considered as the main source of the metric fixed point theory. And it is the most widely applied fixed point result in many branches of mathematics because it requires the structure of complete metric space with constructing condition on the map which is easy to test in this setting. And the Banach fixed point theorem or contraction theorem concerns certain mapping or contractions of a complete matrix space into itself. And it states conditions sufficient for the existence and uniqueness of a fixed point. That means point that is mapped onto itself. And the theorem also gives an iterative process by which we can obtain approximations to the fixed point and error bounds, and which had already done by Giamali sir also. And this paper especially deals with the survey work of Banach contraction principle. That means new results are not included here. Simply survey has done here. And about the different fields like linear algebraic equations, ordinary differential equations, and integral equations as far as possible. And these are keywords. Now let's go to introduction. Metric space. It was given by Brooks and Smith, 2009. Given a set X, a metric on X is a function, also called distance, d from x by x to the r plus is equal to 0, 1. That is xy is greater than or equal to 0 for all xy belongs to x. Distance xy is equal to distance yx, that is symmetric property, for all xy belongs to x. And distance xy is equal to 0 means self distance is equal to 0 if and only if x is equal to y. And the last one is distance xy is less than or equal to distance xz plus distance yz for all xyz belongs to 0. And the last requirement is called the triangle inequality, and we call the pair x the metric space. Frequently we use x to represent the pair now onwards. Now example by 0.80, 2008, consider the usual matrix RD is defined by fx is equal to x by a plus b for all x belongs to r. Then f is contraction on r if a greater than 1, and the solution of the equation x minus fx is equal to 0 is equal to x is equal to ab by a minus 1. And another example, if f is defined as a real number given by fx is equal to x square minus 7x plus 12, we know that x is equal to 3 and 4 are the roots of the given equation, and let's consider fx is equal to x, then x is equal to 3 and x is equal to 4. There are two fixed points of fx. Now, relation between roots and fixed point, it was by Panthi, Jha and Jha, 2013. Sorry, that is 2013. Let fx be a continuous function and fx is equal to 0. This is written as the fx plus x is equal to x, and which is the functional equation, and therefore we have tx is equal to x, and the point x is equal to x naught is the solution of the equation, and then x naught is the fixed point of that t. And it is, and for example, consider fx is equal to x cube minus 2x minus 1 is equal to 0, for which f2 is equal to 3, f minus 2 is equal to minus 5, and f2 into f minus 2 is equal to minus 15 is less than 0. And so the solution of the given equation lies in the interval minus 2 to 2. And this equation can be written as x is equal to tx is equal to 1 by x square minus 2. Then for x is equal to minus x, we have t minus 1 is equal to minus 1. Therefore, x is equal to minus 1 is the fixed point of the t, which is also the solution of the given equation. And this technique for getting root is quite common in numerical analysis.
Respected chairperson, all the respected professors, my respected teachers, and all the participants. This is Vijay Adhikari, MPhil student of Kathmandu University. I am presenting here entitled Bolzano-Weierstrass theorem and its application. I am showing here exposition of Bolzano-Weierstrass theorem and its application. And the outline of my study, description, introduction with biography, different methods to prove with method steps, some application and references. This is the statement of the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem asserts that every bounded sequence of a real number has a convergent subsequence. More generally, it states that if X is a closed bounded subset of Rn, then every sequence in X has subsequence that converge to a point in X. This is the statement of the Bolzano-Weierstrass theorem. Some biography of Bernard Bolzano. and I take a photograph of Bernard Placidus Joan Nepomuk Bolzano, and his date of birth and date of death are given here. Bernard Bolzano was a Czech mathematician, theologian, philosopher, and logician. His logical analysis of mathematical problems made him a pioneer of geometry and calculus and some major works. Bolzano's first work in the field of mathematics was his 1804 doctoral dissertation on geometry, in which he attempted to solve Euclid's parallel postulates. Then these are only some major works. He was also the first person to attempt to prove the theory of continuous simple closed curves, which would later be called the Jordan-Curve theorem. Then Bolzano is mostly remembered for the Bolzano-Weierstrass theorem, which Carl Weierstrass developed independently and published years after Bolzano's first proof. After the Bolzano first proofs, then Carl Weierstrass developed independently. It was initially called the Weierstrass theorem until historian of mathematician uncovered Bolzano's earlier work, Theodor Wilhelm Weierstrass. Carl Weierstrass was a German mathematician who, for his contribution to mathematics, is often regarded as father of modern analysis. The first detailed definition of fundamental concepts like differentiability, limit continuity, and converge were also given by him. The epsilon delta definition of derivative limit continuity was given by Carl Weierstrass. Then the major works: Carl Weierstrass devised test for convergence of series, Weierstrass Young test, and contributed to the theory of periodic function, function of real variable, elliptic function, abelian function, converging infinite product, as well as the calculus of variation. The theory of bilinear and quadratic form was also advanced by him. I take small s and capital S. This sequence has lower bound s and upper bound s. Then we split the interval. We partition, we halved. We take first interval I1 SS as the first interval for the sequence of nested intervals. Then we split I1 at the mid into two equally sized subinterval. It is our construction. We divide two equally sized intervals. Then we give the second interval I2. Then we split I2 again at the mid into two equally sized intervals. Then also we obtain I3. And by induction, we continue this process infinitely many times. Thus we get a sequence of nested intervals. Then there is a number x, which is interval in, is an limit point of action. Then the Bolzano-Weierstrass theorem has a wide application. It is the fundamental theorem, basic theorem of analysis. It has many applications. Some of the applications are here pointed. As an application of the Bolzano-Weierstrass theorem, we prove the Cantor intersection theorem. And then the Bolzano-Weierstrass theorem will be helpful for the following examples. Every continuous function as closed boundary interval is bounded. It is proved by using Bolzano-Weierstrass theorem. Then we find the distance between the closed bounded set and closed set in RL. Similarly, a nested intersection of a sequence of non-empty closed bounded subset of RL is non-empty. Then application to economics. The Bolzano-Weierstrass theorem is also applied for the economics. That is Pareto efficient allocation. As an application of the Bolzano-Weierstrass theorem, we prove the Hahn-Burrell theorem, and similar approach is used in bisection method for numeric analysis. Then these are differences. Thank you.
Session chairs and other friends. I am Chittapani Pokhels from Himalaya College of Engineering. I am going to present the last present of these sessions and these days also. My talks are preponed from the thought to these evenings, so I try to finish my presentation as far as possible. So this is the conformal matrix and its parameters. The slight definition discussion we discuss about the introduction of conformal matrix, slight definition from the original classical definition of matrix, and some use the some complex operators and define the fullbacks and the curvature of the matrix. This is the very definition we know everybody about it. The problem with this classical definition of matrix is that it does not interact well with the calculus. Well, the matrix means it measures the distance. The problem is that if our domain is not convex, then we cannot define the minimum distance by the straight lines. So we have to find the minimum distance. If we talk about the minimum distance, we need the calculus. And this matrix function does not interact well with the calculus. Another is the curvature. Curvature means the rate of change of tangent vectors. And this also needs the calculus. So here is the classical definition of the arc length. If our function is continuous or piecewise continuous, then this is the classical way to define the arc length in calculus. We know everything about it. But here is the problem is that the definition of the arc length totally depends on the measurement of the tangent vectors. The Riemann's insight in the differential geometry was that we can define a new way of matrix. Here, in the conformal matrix, we define the length of the tangent vector. It depends on the measurement. At what point we measure the length of the tangent vector. That means the length of the tangent vector depends on the at which point you are going to measure it. That is the principal definition of the conformal matrix. This is the definition. If omega is a domain of the complex planes, we have planar domain banaeko मैले यहाँ. Then a conformal matrix on omega is the continuously functions rho, which is positive, which is twice continuously differentiable. We need the calculus here. So that if and xi belongs this is a vector, then we define the length of this point xi at the point z. If we vary the point, the length of the xi is going to be changed. That is the length of the xi is equal to just rho of z times Euclidean distance of the xi. So if the rho is different, the length of the xi is going to be changed. That is the definition of the conformal matrix. Where xi denotes the Euclidean distance of the xi point. There are some examples. If we take the domains is whole complex plane, there is no problem. And if rho z equal to, for them, rho z equal to, yes, if rho equal to identity matrix, that means rho z equal to 1 for every well, then we go to the Euclidean matrix. If rho is different, if we take the, this is the unit x, and rho equal to 1 upon 1 minus z square, it is completely continuous functions. It is called the Poincare matrix. And the Poincare matrix, then what is the point length of xi at the point different point. I'm going to repeat the point measure गरेको छु. यो 2 plus 0i भनेको 2 मा यसको मेजर गर्दाखेरि हाम्रो चाहिँ ठ्याक्कै xi आएन हो यहाँ चेन्ज भयो यसको लेन्थ 4 upon 3 upon xi हुन्छ क्याल्कुलेसन गरेर हेर्दाखेरि त्यो Poincare matrixले मेजर गर्दाखेरि त्यस्तै चाहिँ रो मा 0 मा गर्यो भने ठ्याक्कै ओरिजिनल लेन्थ आउने भयो चेन्ज हुँदै भयो त्यहाँ माथि चाहिँ xi को पोइन्ट फरक परिरहेको छ तर पनि मैले 0.9i भनेको इमेजिनरी एक्सिसमा मेजर गरे हो यसको भ्यालु लगभग चाहिँ हाम्रो चाहिँ 5.26 टाइम्स xi भनेर आउँछ भनेपछि पोइन्ट डिफरेन्ट हुँदा बित्तिकै मेजरमेन्ट डिफरेन्ट भइरहेछ द्याट्स व्हाई इट इज कल्ड द कन्फर्मल म्याट्रिक्स द टेन्जेन्ट भेक्टर डिपेन्ड्स अन द एट व्हिच पोइन्ट यु आर गोइङ टु मेजर द लेन्थ यहाँ अलिकति अर्को डिस्टेन्स यो लेन्थ टेन्जेन्ट भेक्टरको लेन्थ पनि यहाँ हेरौँ इटाटी र युनिटी भन्ने दुईटा सिम्पल फंक्सन ल्याएको छु मैले we took out in the unit x d, then under the Poincare matrix, rho z equal to 1 upon 1 minus z squared. The length of the tangent vectors, these are 1 upon 1 minus t squared, means it depends on the function of t value को त्यो त्यसो जाने भयो अनि म्यु मा हेर्दाखेरि 4 upon 3 minus t squared हो टेन्जेन्ट अब यो फुल ब्याक डिफाइन गरेको छु यो यसको मेन इम्पोर्टेन्ट यही हो फुल ब्याक भनेको हाम्रो दुईटा डोमेन छ लास्ट डोमेन ओमेगा 2 मा चाहिँ हाम्रो एउटा म्याट्रिक्स डिफाइन गरेको छ भने त्यो म्याट्रिक्सले चाहिँ डोमेन 1 मा कन्फर्मल फंक्सन छ भने हाम्रो चाहिँ होलोमोर्फिक फंक्सन छ नि त्यसले अर्को म्याट्रिक्स चाहिँ इन्ड्युस गर्छ द्याट्स व्हाई इट इज कल्ड द फुल ब्याक म्याट्रिक्स भनेर भनेको छ रो 2 मा चाहिँ हाम्रो चाहिँ ओमेगा 2 मा चाहिँ रो भन्ने म्याट्रिक्स छ भने त्यो म्याट्रिक्सले ओमेगा 1 मा अर्को कन्फर्मल म्याट्रिक्स इन्ड्युस गर्छ तानेर लगेको गरेर फुल ब्याक भने हो ओमेगा 2 बाट ओमेगा 1 मा जान्छ डिफाइन चाहिँ हामीले कसरी गरेका छौं thus rho of fz कहिले मल्टिप्लाई गर्ने भने डेरिभेटिभ अफ f with respect to z भने पनि हुन्छ प्राइम अफ z थाहा भयो अथवा पार्शियल डेरिभेटिभ अफ f with respect to z बार गर्यो भने चाहिँ यो म्याट्रिक्स हुन्छ यसलाई चाहिँ हामीले फुल ब्याक म्याट्रिक्स भन्छ अब यो चाहिँ कर्वेचर सम म्याट्रिक्सको कर्वेचर हेर्नु यो दुईटा म्याट्रिक्सको इक्विड प्लेनमा डोमेन इक्विडेड म्याट्रिक्स हो भने चाहिँ हाम्रो चाहिँ के हुन्छ कर्वेचर 0 स्ट्रेट लाइन हुन्छ बेन्डिङ गर्दा नि स्ट्रेट लाइन हैन हाम्रो रो j = 1 र भने स्ट्रेट भयो स्ट्रेट लाइन सर्टेन स्ट्रेट भने हाम्रो स्ट्रेट लाइन हुन्छ स्ट्रेट लाइनमा चाहिँ हाम्रो बेन्डिङ हुँदैन बेन्डिङ नभएपछि त्यसको कर्वेचर लगभग 0 हो हाम्रो डेफिनेसनले म्याच गर्छ वी डु नट drawn from the our basic definition त्यस्तै स्फेरिकल म्याट्रिक राख्यो भनेपछि होल कम्प्लेक्स प्लेनमा 1/1 + z² गराउने यसलाई स्फेरिकल म्याट्रिक भन्छ हामीले चाहिँ अलिकति डिफरेन्शियल ज्योमेट्री तिर रिमानेन्ट ज्योमेट्री भयो भनेपछि पोजिटिभ कर्वेचर एउटा मात्रै स्पेसको चाहिँ पोजिटिभ कर्वेचर त्यो भनेको स्फियर अथवा त्योसँग होमोमेट्रिक स्फियरको चाहिँ जहिले पनि पोजिटिभ कर्वेचर हुन्छ हाम्रो यो चाहिँ डिफरेन्शियल ज्योमेट्री यसलाई ज्योमेट्रिक फंक्सन थ्योरी भन्छ एक्चुअली यो we study the complex variable with the help of the differential geometry that's why it is called the differential geometric analysis in fact अब यही concurrent matrix को चाहिँ त्यो फर्मुला लगाएर मैले यहाँ मैले डिटेल त देखाइन if anybody need I have the full homework of this and let the unit को चाहिँ म्याट्रिक्स निकाल्यो भने चाहिँ नेगेटिभ कर्वेचर छ यसको इम्पोर्टेन्ट भनेको चाहिँ इट वाज द फर्स्ट अल्फोर्सले चाहिँ डिजाइन गरेको हामीले सबैले पढाएको छौँ पछि स्वार्ट्जलेमा भनेर पढाएको छौँ स्वार्ट्जलेमा भनेको यो थ्योरम स्टडी गर्दाखेरि कर्वेचर यो कन्फर्मल म्याट्रिक्सबाट गयो भने चाहिँ इट इज जस्ट अबाउट द इनइक्वालिटिज अफ कर्वेचर अनि त्यसबाट हाम्रो कम्प्लेक्स भेरिएबल भएको जति फङ्सनहरू छन् ल्युलिस थ्योरमहरू सबै चाहिँ यो कर्वेचरबाट सबै डिफाइन चाहिँ गर्न सकिन्छ अब अरू चाहिँ वास्तवमा यो प्रेजेन्टेसन भन्दैन यो वर्कसप गर्ने टाइपको हो कन्फर्म म्याट्रिक्समा अब कर्वेचरहरू कसरी जान्छ कम्प्लेक्स एनालाइसिसलाई कन्फर्म म्याट्रिक्स हामीले कसरी स्टडी गर्न सकिन्छ भनिन्छ मैले एकदम छोटो टाइममा टाइम बेसी जाए जस्तो लाग्छ अलिकति सेभ गरेँ थ्याङ्क यू भेरी मच